Hi everybody, welcome back. In the last video we talked about the beginning of understanding how our solar system formed, particularly by looking at how stars form in general and how planets form in general. In this video we're going to look more particularly about how our solar system formed and what implications that would have on its eventual composition. So we discussed how planetesimals were constructed by collisions between solid particles, and this whole point of accretion is that only solid particles are able to accrete. In other words, not hydrogen, not helium. We're talking about sandy, dusty types of particles and particles composed of molecules and or combinations with heavier elements. So that's something to keep in mind here. Now, as this accretion continued, you ended up getting larger objects until eventually what you would eventually have would be a handful of large planets and a number of leftover planetesimals. On our solar system, those would become asteroids and comets, and that's why astronomers are so interested in learning more about asteroids and comets, because these are relics from the initial formation of our solar system. But yeah, again, this process of growth by accumulation, which eventually builds planets, is what we call accretion. Again, just don't confuse it with accretion disks around black holes. Those are completely different types of accretion disks that form in a different way. Now, in our case, most of our solar system's material was swept up during the first 100 million years, generally probably less, of our solar system's existence. And this was what you could call the heavy bombardment. Now, there is a lot of evidence that there was another major period of what you could call accretion, where there were a lot of collisions between the planets and somewhat large bodies like asteroids and comets about 4 billion years ago. And that's known as the late heavy bombardment. And how this occurred is something that we will discuss soon. But in any case, many smaller objects would get destroyed by collisions, and the resulting debris would be swept up by the large planets. Now, the exact process by which this occurs and the exact characteristics that a new solar system is going to have is something that we can kind of estimate with computer simulations. And this is highly dependent on things like the initial angular momentum of the system, the average density as a function of position, and those sorts of things in the newly forming disk. So that's why not all newly forming systems are going to be the same, even if they form around the same massive star. Now, one of the results that we get from these computer simulations is we believe that our system had more planets initially. In particular, we think we probably had 5 giant planets, at least 5 giant planets, and that one of these was ejected or collided with another planet due to these interactions that occurred during our early solar system. So, also, a nice thing about these simulations is that they suggest something that we know to be true, that you should have regions like the Kuiper Belt, this area of large comet-like bodies, things like Pluto, past the orbit of Neptune, and also a big spherical cloud of small comet-like bodies way, way past the Kuiper Belt, known as the Oort cloud. This is a result of computer simulations, and we know that it's there. We knew that it was there statistically over 70 years ago. Now, material left over from the formation of the planets went into forming the Kuiper Belt and Oort cloud. Essentially, the Kuiper Belt is a region of planetesimals and comets outside of Neptune's orbit, with Pluto being the largest and most well-known example of a Kuiper Belt object. But it also contains other large comets as well as other dwarf planets and stuff like that. But essentially, the overall density in this area was never large enough to collapse and form a planet, and there was also a lot of scattering of icy bodies by Uranus and Neptune once they migrated out to their present orbits. Now, Comet Hale-Bopp is an example of a Kuiper Belt comet. This was a very long-lived comet that visited the inner solar system back in the late 1990s. In particular, 1997 was the main year of Comet Hale-Bopp, and it was quite bright for a very long period of time. It's the only comet in recorded history that was visible to the unaided eye for over a year. Usually they're visible to the unaided eye for like days or weeks, but this thing was visible to the unaided eye for over a year. The reason is because it was much bigger than a typical comet. I mean, this thing was something like 70 miles wide, whereas a typical comet might be something like 6 miles wide. So this was quite a large icy body, and it came from the Kuiper Belt. Now, the Oort cloud is this region of generally much smaller planetesimals, very far outside of things like Pluto and Aries and stuff like that. The Kuiper Belt is shaped kind of like a disk or torus, whereas the Oort cloud is shaped like really a sphere. And you're dealing with a bunch of small objects with relatively random orbits that are very, very far away. So that's the big thing to keep in mind with the Oort cloud. We're talking about trillions of cometary nuclei. But the thing is so big, we're talking about tens of thousands of astronomical units that collisions between these objects don't really occur. Comet Hyakutake, which visited the inner solar system in 1996, is probably an Oort cloud comet. But unlike the Kuiper Belt, the Oort cloud, again, is a spherical cloud of comets, whereas the Kuiper Belt, that's actually something that occurred due to more organized scattering somewhat with interactions of Uranus and Neptune. A lot of the bodies in the Oort cloud were scattered out early on by interacting with Jupiter and Saturn, very early in the solar system. But the idea is that these types of interactions with such much more massive bodies are going to cause objects to get deflected at a very high rate of speed and in somewhat random directions. So that's why the Oort cloud is more of a spherical body. And also, it's somewhat of a remnant of the initial stages of the beginning of planet formation as well. Here's a picture of Comet Hyakutake, which we think came from the Oort cloud. And generally speaking, the long period comets came from the Oort cloud. Comets with orbital periods on the order of like tens of thousands or hundreds of thousands of years came from the Oort cloud, whereas comets with orbital periods on the order of tens of years to hundreds of years generally come from the Kuiper Belt. Now, initial studies of isotope abundances suggest that Kuiper Belt comets actually provided Earth with some of its water early in our solar system's formation. And the general idea is that Earth got its water from comets. That was the general idea. And that maybe the Oort cloud provided some water, but in smaller amounts. But as we started looking at these isotope abundances in more detail, with greater degrees of precision, with newer instruments, we realized that this really doesn't match the isotope abundances that Earth's oceans have. In particular, we're talking about the ratio of deuterium, that is, heavy hydrogen in the water, compared with ordinary hydrogen in the water. And we realized that actually a better match comes from the region of the asteroid belt between Mars and Jupiter. So we now currently believe that we probably got our initial water from that region of the asteroid belt between Mars and Jupiter. We'll have more to say about the asteroid belt later in this unit. But that's something to keep in mind as one of these big results of recent planetary astronomy in our solar system, the realization that we actually probably got our water from the asteroid belt, which seems kind of strange because of the fact that most of those bodies there are pretty rocky, but not all of them. I mean, something that we'll discuss later on is that the asteroid Ceres, the only one that is officially called a dwarf planet in that region, that actually has quite a bit of water and ice. But we're now realizing that Ceres may have formed farther out in the solar system and eventually migrated there. So that's one of the other kind of cool results. But there are other bodies that probably did the same thing, and some of these may have given Earth its water early on. So now let's get into a summary of the formation of the actual planetary bodies in our solar system, because this is one of the big important points in this entire discussion. How does our understanding of solar system formation agree with our knowledge of the planets themselves? So first of all, Jupiter. Why is Jupiter so big? Well, Jupiter formed first. The reason it formed first and the reason it became biggest is because Jupiter formed just beyond what we call the frost line. The frost line is the division inside of which substances that we consider to be volatile substances, like water, methane, carbon dioxide, carbon monoxide, etc. Inside of that region, they would be close enough to the sun that the temperatures would be warm enough that they would become gaseous. But remember the big point that we made at the beginning of the video. Solids are what participate in accretion. Gases don't. Gaseous particles will just bounce off of these planetesimals and escape. They won't get accreted. But solids will. So Jupiter first started off as a solid body, a kind of rocky body with a core of maybe like 14 to 18 times the mass of Earth. But thing is, why did Jupiter become so massive as opposed to, say, like Saturn or Neptune? In other words, others that also had large rocky cores. Well, consider this fact. Remember that our Sun formed in its location in the presolar nebula because that's where it was densest. The closer you were to the Sun, the denser the material was going to be. But here's the thing. The closer you are to the Sun, the more likely that material is going to be gaseous, which means it's not going to accrete. That's why the inner planets are rocky, because the rocky stuff is the stuff that didn't become gaseous, whereas the gaseous stuff didn't accrete. And it was too hot at that time really to hold on to a really substantial atmosphere from that gaseous stuff. On the other hand, outside of the frost line, outside of 4 astronomical units, the substances that we think of as volatile substances, particularly water, which was very, very common. Water is a very common substance all throughout our galaxy, and indeed all throughout the universe as far as we can tell. Outside of the frost line, this was solid. It was able to participate in the accretion. So after you got that big solid core, well, it just kept accumulating more and more mass because here the water is solid, so it participates in the accretion as well. And remember, the closer you are to the sun, the denser the region is. So if you're trying to form the biggest, most massive planets you possibly can, what you want to do is you want to be as close to the sun as possible, but just outside of the frost line. Close enough where it's dense, but far enough away that the stuff is solid. So that's why Jupiter formed there. Now, in truth, Jupiter probably formed somewhat farther out than it currently is, but there was a lot of migration going on in the early part of the solar system. But still, it formed somewhat out of the frost line, outside of the frost line. And as a result, it accumulated a whole lot of mass very early. Well, not surprisingly, Saturn, the second most massive planet in the solar system, was also the second planet to form. We used to think that the ring system may be very old, and there's still some researchers who believe that, though nowadays we think that the ring system of Saturn is actually quite young, maybe as little as 100 million years old or less. Or at least its current ring system, I should say. Uranus and Neptune probably formed initially closer to the Sun, and for that matter closer to Saturn, and then migrated farther out due to gravitational interactions between those giant planets. And there's a number of lines of evidence for this. One is that otherwise you wouldn't get massive cores forming, particularly for Neptune, because, I mean, Neptune does, we believe, have a massive core, but if it formed at its current location of 30 AUs, it shouldn't have been able to accumulate a massive core. Luckily, computer simulations show these types of migrations occurring, so they are quite consistent with what we see in our simulations. But it's also, again, the simulations are consistent with the observational evidence. Chemical composition of these bodies is also more indicative of formation, at least somewhat close to the Sun. And finally, the 2004 Nice model, named after the city Nice in France, not like your niece and nephew, but city Nice. This was a group of computer simulations showing not only this migration, but also the interactions between these migrating outer giant planets like Uranus and Neptune with the objects of the early Kuiper belt, which not only kind of cast some of them out more toward their present locations, a little farther out, but also a whole bunch of them toward the inner part of the solar system, which would explain the late heavy bombardment that began about 4 billion years ago and peaked probably about 3.9 billion years ago, where there were a whole lot of giant impacts that occurred during that time, and you can still see evidence for those when you look at Mercury, our moon, as well as a number of other moons in the solar system, particularly large ones like Saturn's moon Rhea or Mimas or things like that. Now, inside of the frost line, remember things that we think of as volatiles, which also tend to have lower density. They were gaseous, so they didn't participate in accretion. The only things that participated in the accretion and the formation of planets were the materials of higher density, rocky materials. That's why the inner planets have higher density. And there was a continuation of merging and making larger planets that occurred for probably about 100 million years. And one of the latest of those collisions was actually between Earth and a Mars-sized body that is often called Theia, that resulted in the creation of our moon by scraping off Earth's outer crust. Here's a picture of our moon, of course, and you'll notice a whole lot of impact craters here, particularly a lot of the old ones that look somewhat more, quote, weathered than the other ones that have more clearly defined ridges. A lot of those came from the late heavy bombardment. And then, of course, there was the earlier, just heavy bombardment that resulted in the creation of our moon about 4.5 billion years ago, when a Mars-sized object collided with Earth at some sort of angle that resulted in Earth temporarily getting a ring, out of which condensed our moon after a while of collisions. And our moon's been around ever since. Now, even today, Earth continues to sweep up many tons of material every day in the process of accretion. So whenever you see a meteor streak across the sky, you are watching accretion. So here's a nice picture of a meteor going through, as you can see, the Hyades and Taurus. There are the Pleiades right there. Oh, what's this bright object? Yeah, that's a planet. That's actually the planet Saturn. This picture was taken about 20 years ago when Saturn was in Taurus. Now, it turns out that we can't predict the orbits of the planets with a whole lot of accuracy on timescales all that much longer than about 100 million years. For example, Mercury in particular is a little bit unstable. Pluto, way out there, is actually known to have a chaotic orbit on a timescale on the order of about 20 million years or so. So who knows, maybe in about 30 or 40 million years it could actually collide with Neptune or be scattered into some other place in the outer solar system. And also, Mercury's orbit, as I mentioned, is unstable. In fact, it could end up colliding with Venus or even Earth, though this is a bit unlikely. Now we need to turn our attention to kind of summarizing our understanding of how the different planets with their different characteristics formed and why they have those characteristics. So the local temperature, that is the temperature having to do with the object's position from the sun, is going to determine what materials are solids. If the temperature is higher, you're going to be dealing with things that are more like metals and rocks, things that we think of as metals and rocks, that is. And then a bit cooler than that, you can deal with things like water ice. And then really far out, you're talking about methane ice, which is probably why Uranus and Neptune have quite a bit more methane in their atmospheres than do Jupiter and Saturn, which formed closer to the sun. Now, solid objects, again, are what participate in the accretion process, whereas gaseous molecules just bounce off, unless the object already has enough mass to hold on to those gaseous molecules and form an atmosphere. That's why Jupiter and Saturn are so much more massive than everything else, because they accumulated so much more mass quickly enough that they were able to pull in a lot of that hydrogen and helium that was the dominant stuff in the early solar system. In fact, everywhere, because remember, hydrogen and helium are the most common elements in the universe. So, yeah, close to the sun, you're dealing with objects formed out of silicates and rocky material. Farther out, a lot more water ice. In particular, like Uranus might have several Earth masses worth of water ice, as well as other ices like methane ice, ammonia ice, etc. So there we go. If you're too close to the sun, like 0.0 something astronomical units, then even things that we think of as rocky stuff, those are going to be vaporized. And that's why Mercury isn't a lot closer to the sun than it actually is. So this whole idea is known as equilibrium condensation theory. So it really matches quite well with our understanding of the solar system and the actual visible characteristics of the planets, with the fact that the closer ones to the sun are denser, the farther ones out are much less dense, but the closest among those are the ones that are most massive. Now, how do you account for situations where we're dealing with solar systems where that's not true? Well, again, planetary migration is also a big deal. If there's a lot more gas or the distribution is a bit different in that early forming system, then friction can slow down, say, giant planets and show them appearing, say, close to their stars. That's rare, but when it happens, it's very noticeable. So we've mentioned a whole lot concerning the ages of processes, how long ago certain processes occurred, and how old our solar system is. How do we know such things? Well, determining the age of our solar system, in fact, the ages of bodies in general, particularly using radioisotope dating, is quite an important skill, and that's something that we are going to look at in the next video. So I hope to see you then, and thank you for watching.